it's not going to be, well, I mean, it might be, but it's unfamiliar to me as far as teaching is concerned. So this is not going to be necessarily like a, you know, an A-level lesson. It's kind of more relaxed than that. So let's just see where this goes. Do not expect today like a full-blown like mathematical treatment of quantum physics, because that's not what I'm going to do. And maybe next week we can get into that. Today I just want to give you an introduction to the wave function and get towards talking about uncertainty. This idea that you can't know the position and momentum simultaneously, because you can actually get there without doing any maths at all. So I'm going to share my screen on the iPad because I've put a few pictures up here to help me. Now, we've got a mix of people here. Why is that not working? We've got a mix of people here. We've got some second years who've covered more physics than the first years. So if there's anything at all that's unclear throughout, I don't mind if people want to fire away with questions as we go along. Clearly, I'm not going to be able to cover every single last detail, and I'm not going to start talking about, like, for instance, the photoelectric effect in detail. If you've not covered that yet, you will. Where I'm going to start from is by suggesting that up to now, if you're in the first year, you'll have covered waves and you'll have covered particles. You'll have just got into that. And you'll shortly come across an idea called wave-particle duality, which the first time you come across this really is when you come across phenomena which go against a particular model. So for instance, the photoelectric effect that you'll study in the first year or have studied can't be explained using a wave model for light. You need to actually consider light as behaving in a particle manner, and you need to consider it as being composed of photons. So literally you have to sort of think of a ray of light, let's say a red beam, as being composed of in sort of, you know, discrete bundles of energy, which we call photons. I'm not going to go into the detail of that, but this suggests that light is neither fully a wave, because you can't describe the photoelectric effect with that model, or fully as a particle, because you can't describe refraction and interference, double slit experiment, for instance, using a particle model. Similarly, an electron, now this is a famous experiment, an electron, when fired through a pair of slits, classically what you'd expect, if you fired billiard balls through two slits, you'd expect a distribution to be something like this. You get a pile of balls here and a pile of balls here. So this was number of electrons. But what you get if you do the experiment is an interference pattern, which is this here. Now, again, the first years among you won't have covered interference necessarily, but what you're going to learn is that when you have two wave sources or more wave sources, you get interference because the maxima of the two sources, the maxima of the waves of the two sources can either add constructively or add destructively. So you get an interference pattern typically when you have more than one source being shone at a screen. So what's strange about this is that this is an example of an electron or electrons behaving in a wave-like manner. Okay. And what's even stranger, and again, I'm not going to go into the detail right now, is that if you do the experiment without observing which slits each electron goes through, you get an interference pattern. But if you set the apparatus up so that you know which, which slit an individual electron actually went through, so you measure the electron's position at that point, the electrons go back to just producing 2 piles of electrons on the screen. So this is bizarre because it seems there's some, you know, observation affects the system, which it does. You might think, okay, maybe the electrons, maybe you've got loads of electrons bouncing off each other, and that's what causes interference. But the thing is, if you do it 1 electron at a time, so just fire individual electrons through 2 slits, you still get, let's see if this plays, you still get an interference
pattern. Now we are looking at the detector pane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding 1 electrons are detected on distribution. This experiment.
Oh, I didn't mean to do that. So you can see,
since this experiment lasted for more than 30 minutes,
but there's a pattern there.
I have
it's not perfect, right? You're not getting, you know, perfect maxima and then absolutely nothing, but you can see that there's something going on there beyond electrons hitting uniformly or in 2 piles. And that is even though we're firing 1 electron through at a time. So then you ask, like, how on earth can an electron interfere with itself? So let me go back to this page. So we've got this problem. Is an electron, is light, wave or particle? The answer is it's neither. And those of you who I've taught are familiar with this. So this is a fairly silly way of thinking of wave-particle duality, in the sense that if all these people are blindfolded and they're trying to work out what this object is, depending on how they look at it and where they are and what experiments they do on it, they're going to think different things. So if you're next to the side of the elephant, you're going to think it's a wall because it's round and flat. If you're at the tail, you might think, oh, this is like moving about and it's long and thin, a rope. So why is this relevant? Well, an electron is not a particle nor a wave. It's an electron. Particle and wave are just labels we ascribe to it depending on how we measure it or on how we observe it. So it's almost like we're looking at the electron through a certain filter or lens, which makes it appear to us to fit a particle model. The truth is an electron is an electron. Electromagnetic radiation is electromagnetic radiation. If anything, they're what you might call a quantum object. You can't just call them plain particle, plain wave. So that's the first thing. And these phenomena were the stimulus for us rethinking our approach. Okay, any questions so far? Don't worry if not. I don't mind if you just want to sit here, do something else and listen to me, in all honesty. I'm going to record this anyway. Next. So what you'll learn about these 2 effects over the course of the A-level course. Next, I want to talk about classical mechanics. So you've learned Newton's laws, haven't you? And at A-level, and in fact, in most situations, mechanics, you can talk classically. And what does that mean? Well, what it means is that we can define the state of a particle or any system by specifying 2 variables: the position of each particle and the momentum of each particle. That is literally all we need to specify the state of a classical system at any point in time. And, you know, then you can work using these things. You can work out things like the energy, which is a function of distance or position and momentum. You can work out things like angular momentum, which is a function of position and momentum. So position and momentum are like fundamental variables And then all the other stuff, energy, angular momentum, GPE, are functions of those two things. So how does classical mechanics work? So in classical mechanics, you work out the future, or you work out the future state of a system by using two equations. One, you already know, F equals ma. In fact, both of them you already know. And, well, the other one, well, let's start with F equals ma. So F equals ma is really something that can be written F equals m dv by dt. Now, dv by dt, hopefully the first year you've done differentiation. So that's just a way of writing acceleration as a rate of change of velocity. And further, you can rewrite this F equals dp by dt. So you notice how this p, the momentum, which is fundamental, appears here. So we've got an equation which tells us how p varies and develops as time progresses. So if we know p initially, we can use Newton's second law to work out what p is in the future, as long as we know what forces are acting. As long as we know the forces acting, we can work out what p is going to do sometime later. What about position? Don't we need an equation which will tell us what x is going to do as time progresses? Well, of course we do. And that equation, which is comprehensible by everyone, I think, is mv. Momentum is mass times velocity, which is also written m dx by dt. So look at this. I've written down classical mechanics in two equations. That's all you need, literally. Newton's second law, the equation for p, what p does as time goes on, and then you need a second equation to get the x in there. And with these two equations, you can work out the future of a classical system. Work out future state. Now, you might not have heard classical mechanics described in that way quite, but that is more or less Newtonian mechanics. That's how the universe operates. Any system is a bunch of positions and momenta. You grind the handle of those equations that I've boxed, and then you find out what happens in the future. Okay, it's deterministic as well, because you can run those equations backwards. You know, if you know the position and momentum of every single particle, you can work out the future state if you know the forces. So that's classical. Next, I've not left myself much space here. Next, we've got quantum mechanics. Now, you know what I'm going to do, just for the fun of it, is cross out the word quantum and put real instead, because, you know, quantum mechanics, it makes it sound like it's some kind of exotic, I don't know, something too exotic, right, to imagine. It's just the real world, because it's a more precise, accurate representation of what the world's actually like. In the real world, it turns out that you can't know the position and the momentum at the same time to an arbitrary degree of precision. So this is a rough statement of what is called the uncertainty principle. So you don't, I mean, I'm not going to write all this down. You can't know X and P simultaneously, right? I'm going to just explore that down here. That's a problem, because if classical mechanics requires us to know X, the position of every particle, and P, the momentum of every particle, well, if we can't know both simultaneously, then we're not going to be able to proceed using these equations, right? That's a major problem. If you don't know what X and P are, you can't, where do you start? So, different approach required. So let's just draw a line between here and here. So I'm going to make some postulates. And when I say postulates, I mean let's sort of assumptions, if you like. Let's make some assumptions. We're going to make some postulates of quantum mechanics. One is that the state of a system, so you can just take these as postulates. We're going to state them and then see where this leads to. The state of a system is no longer given by X, the position and of all the particles, and P representing like the momenta of all the particles. It's given by, it's completely specified by the wave function. Just a mathematical function, which is given the symbol lambda. Okay, so it's just, all it is, as strange as this sounds, it's just a mathematical, which is kind of obvious, mathematical function. So now instead of, imagine you had a load of pool balls on a snooker table, like there's in the common room out there, right? In classical mechanics, you would specify the position and momentum of every ball, write it down and say, that's the state of the system. If you were going to describe that state using quantum mechanics, you would have a wave function, a mathematical function to represent that state. Don't worry about what form the function takes or anything like that, just the general idea. We've got this function which has all the information inside it. For those of you who've done further maths, you might be interested, and this is something you don't need to worry about too much today. It's not just any mathematical function. It turns out that it's a complex function, which means it can take complex values. Complex numbers are a type of number in which we extend the real number line by adding another axis, which is basically in units of the square root of -1, or I. And so you'll then have a plane, a number plane. And I'm not going to teach complex numbers right now, but needless to say, it's a bit like extending from the rationals to all the real numbers. You kind of define a new, bigger set of numbers called the complex numbers. And you might think, well, do complex numbers actually exist? Because I can't have a complex number of torches, right? Or a complex number of pens. I can only have integers. But they do exist. I'm telling you now, you might not believe me. In order to do physics, you need complex numbers. So they do have a reality, even though you can't count using them. Okay, that's postulate number one. Postulate number two is that the square of this function, if you square it, that gives you basically the probability of finding a particle or the quantum object, probability that an object is in the state which is given by the wave function is at position X. So the square of the wave function is what gives us probabilities. I really should have given myself more space here. Let me see if I can. I think I can fix this actually. Maybe not. Okay, never mind. There's a third one, so I'm going to have to go down here. The third postulate, which is kind of, these are sort of like important principles of basic quantum mechanics. And that is that if there are two states that a system can be in, if two states are possible, states of a system, then the state phi1x plus phi2x, literally the sum of the functions with some constants, any linear combination is also a state. Now, this is, you've all heard of the term superposition, right? So this is called, where you add two states together, superposition, just like the superposition you've learned about in waves, if you've got that far, or fields. So let me go back to the pool table analogy. If I found the pool, imagine I set the pool table up so the balls are all in a triangle, and then I break off. So that's one state, right? The pool balls in a triangle and the cue ball on the spot. Then I take the cue shot and the balls go everywhere. That's another state where the balls are sort of randomly arranged. In classical mechanics, and because it's a macroscopic system, but I don't want to get into that now, they're two distinct states. That doesn't really make any sense to think of a superposition of the two. What I'm telling you is that, say you had a system made of multiple electrons, okay, like the electron or the electrons around an atom. If the electrons were in one state, or there was one possible state for them all, and then there was another possible state for them all, the addition of both states would also be a state. Now, obviously, everyday objects can't be in two states simultaneously, or said to be in two states simultaneously. Quantum particles, quantum objects can. Just because we can't picture it doesn't mean it can't happen. Okay, so if you want the headline principles of quantum mechanics, those are the three. So they're quite simple to state. The problem is, and the reason why whole university lecture courses are devoted to the introductory quantum mechanics, is that going from these three things to explaining everything in full mathematical detail is difficult. You need a certain amount of maths behind you to be able to do it. But I'm going to have a go at talking just generally about wave functions, drawing a few, and showing you what the physical interpretation is. Okay, before I continue, any questions on anything? That's as difficult and as technical as things get. From here, it's more descriptive and qualitative. So don't worry if that just sounds like gibberish. There's no way of simplifying that, apart from to use my pool table analogy to try to sort of come up with, yeah, a way of visualizing it. Fire away. Oh, is that someone or not? Okay, wave functions. You will see I've drawn some axes here already. I'm going to draw two wave functions, and I want someone to tell me what the interpretation of them is. So this is position on the x-axis. So we're considering just like a quantum particle, or, you know, a quantum object, let's say, just in one dimension along a line. So I'm going to draw this one, and I'm going to draw this one. So can someone tell me what do they think, what's this object doing? What does this wave function tell us?
It's superposing.
Oh no, these are separate wave functions. So so what does this one on the left tell us
it's
about
the probability that the object is in that position?
So, well, actually the square, so if we square it, so P, when I say Px, I mean wave function squared. Yeah, when we square it, we get the probability. So what this wave function is describing is a particle which is pretty much at position x1, because the wave function's highest there and it's zero everywhere else. So this wave function, we know x is x1, and the uncertainty in that is pretty small. It's pretty well localized, the particle to x1 position, because the wave function spikes and then it's zero everywhere else. Similarly, this other one shows the particle at another position, x2, and again, the uncertainty in position is small. So we'll get a large probability of being at x2. So that's almost the simplest situation you can imagine, isn't it? A particle or object situated at a position in space, a point in space, like a ball sitting on the table. You might think at this point, and I wouldn't blame you, big deal, why did you just draw 4 graphs out? Let me do the next set. Let me draw another wave function, which is perfectly legitimate. And let me draw another one. Now, they are sinusoidal, they're sine waves. What do you think, and you can just have a guess, what kind of object, or what might an object be doing where might an object be in these situations?
Surely it's moving, it's not like stationary.
Okay, moving. Anything else?
Is it moving?
Maybe it's on the end of a spring.
Oh, I see. Oh, well, okay, remember, I know it looks like the SHM, the oscillation, but remember what this is. This is a wave function, a mathematical function. So there's no physical oscillation going on. But you're right, the form of it is very much like a mass on a spring.
Does it have equal chance of being at any of the peaks?
Right. Because if we square this function, you'd expect, and don't copy this down, do not copy this bit down yet. You'd expect it to do this. If you square a sine function, you get sine squared x. So you'd expect the probability of it being here, 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 and here to be the same. It's actually not that. And the reason is, for the second year, first year, because wave functions are complex. When a wave function's like this, you can actually represent it using complex notation as this. And because when I said the probability is phi squared, it's not quite, because when you have a complex function, you need to do the function times its complex conjugate, which means that you get e to the ikx times e to the minus ikx, which is equal to e to the naught, which is 1. So in fact, and again, I'm sorry if you've not come across that, this bit, the p equals 1, is the reason why I'm going to draw a straight line like this. Because actually, because of the nature of the wave function, it turns out that a pure sine wave like that gives a probability of a constant probability everywhere. But it's very similar to what Jessica said. That's not a million miles away. Basically, there's a probability it can be anywhere. Okay. Can someone tell me then what the uncertainty in position is for these cases down here? Or like, how would you describe the uncertainty in the position of the particle?
Is that equal? It could be anywhere.
Yeah. So the uncertainty is huge. So X could be anywhere. Who knows what X is? We have no idea at all. So the uncertainty in position for these wave functions is as big as it could be. It's like infinite, basically, because it could be anywhere. So I've just shown you the two extremes of wave function. I've shown you these ones where the position is very, very well known. Like we could make those peaks as sharper and sharper and sharper. And a wave function where the uncertainty of position is astronomical. Two extremes. So, what next? I want you to recall something. Again, the first years are going to learn this in approximately, well, if they've not already, they're going to learn it by the end of LQ. There is something called a de Broglie wavelength, or de Bruy wavelength, which is equal to something called Planck's constant over the momentum of the particle, h over the momentum. Basically, you can think of the de Bruy wavelength as being like the wavelength associated with a particle. So imagine an electron, you can work out a wavelength of the particle. It's like the wavelength of the wave associated with the particle. This is an important equation because it tells us that if we have a specific wavelength for the particle, one value of lambda, what does that mean for a value of P?
One value.
Yeah, if you've got one value of wavelength, that means you know the wavelength. P has got an exact value. So let me write that down. A specific, this is important, a specific value of lambda implies a specific value of momentum, i.e. with zero uncertainty. So we know P precisely if we've got definite wavelength. I'm very impressed if you're like fully still with me, right? But you might need to go and sort of rewatch some of this later on. I'm going to send this to Mr. Hearn and then he can criticize it because he's the one person who knows the most physics out of anyone, and he'll know if I'm doing a good job. So let's look. So I'm going to repeat this again slowly. A specific value of wavelength implies a specific value of momentum. A specific value of lambda implies a specific value of momentum. Let's look back at this wave function. The one that's on the screen now. Does that have a wavelength?
No.
It doesn't have a wavelength. You can't say this wave function has a wavelength. Can you say this for so this state doesn't have a definite value of momentum. The uncertainty in the momentum is huge. Similarly here, we can't say the wavelength is this, lambda is this. Therefore, we don't have any idea what P is. What about these wave functions? Does this wave function, the one at the top of the screen have appear to have a definite wavelength?
Yeah.
Yeah, we can say it's periodic. We can confidently say that that is a wavelength. Therefore, if it has a definite wavelength, we know what P is to a high degree of precision. Therefore, delta P is small. And similarly for this one, we know the wavelength because it's periodic and it looks like a wave. Hence, the delta P is small. Now, some of you will have clocked this. You'll notice that for the top set of graphs, where I've got a low uncertainty of position, so let's shade that in green, low uncertainty in position, that means that I have to have a high uncertainty in P because there's no definite wavelength. Conversely, at the bottom, where I've got a small, sorry, let's do this the other way around. Conversely, at the bottom, where I've got a huge uncertainty in position, I've got a low uncertainty in momentum. So we're starting to hint at the uncertainty principle here. There's this with wave functions, if you've got good position resolution, the wave function loses its momentum resolution and vice versa, just from the nature of the wave function and the mathematics of it. So you can't have both uncertainties being small. You can't have a wave function which satisfies that. It's impossible. Which is basically I've more or less got to the uncertainty, like the sort of qualitative description of why there is an uncertainty principle for position and momentum. Right, break number 2, questions. Now, I'm going to wait for at least 10 more seconds while getting a glass of water. Okay, now this, for people who've not come across this before, this is like very good physics, but you'll notice that I've not actually used anything yet. I've not thrown any balls around because you can't show this using objects easily. In fact, you can't really do it anyway. Here we go. Let me try this one on you. I can give you another kind of uncertainty principle in a sense. If imagine you were stood here and a wave was traveling past you like that. How could you measure its wavelength? Imagine it was, well, just imagine it was a big wave that looked like that, right? Could you measure its wavelength?
Yes.
Yes, you could go, let's get my ruler out, measure lambda, yippee. How long would you have to wait? So think about the time now that you measure it for, the wave. Like, how long would you have to wait to be entirely certain that the wave would never change and always have that wavelength?
I mean, you have to wait the period t, which is a wave.
If this wave was just continuous and went past me forever, how long would I have to wait to be absolutely certain that the wavelength would never change?
Absolutely certain, it means that you would have to stay
yes.
a long time.
A long time, an infinite amount of time.
Yeah.
So in order to know the wavelength with 0 precision, you would need to wait an infinite amount of time, right? So this is almost a little sort of similar in the sense that you can't know the wavelength. You know, if the time period you measure for is very small, so you've got a low delta t, then your uncertainty in the wavelength will be higher because you've seen less of the continuous wave. So in a strange sense, this situation of whoever this is, this guy down here, measuring the wavelength of a wave is actually kind of can bring you to another kind of a sort of similar uncertainty principle. You can't kind of know the wavelength with, you know, to a high degree of precision over a small time period. But if you make the time period bigger, you can get narrowed down on lambda. Interesting. Anyway, some more maths for you. Have you done, oh, you see, again, I find myself apologizing to the first year all the time. Have you come across standing waves? So, a standing wave, okay, let's, first of all, if you have different, imagine these are sine waves of different wavelengths. So they've got, you know, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. Mathematically, if you add waves like that together, you generate a function which is more tightly packed. It's a wave packet. In order to create wave functions which are more localized, particularly like the one I've got up here, which is just a spike, you need to add together lots of sine waves with different wavelengths. So the fact that in order to make this kind of wave function here, I need to add a load of waves of different wavelengths together means delta lambda is going to be pretty big. And the more I have to squash this down into an even more concentrated area or distance interval, the more of these lambdas I'm going to have to add together. So you're even less knowledgeable about delta lambda. Now, this idea of adding together different sine waves of different wavelengths to generate new functions is not something you'll have come across, but it's something which in maths involves something called Fourier Series or Fourier analysis. Now, if you have a square wave like this, you can approximate that, look, by just a sine wave. Look at those two diagrams. Is this a good approximation for this? Is the blue line a good approximation for the purple line in this example?
No.
No. And so we've only got this wavelength here. If you add, say, this wavelength that we've got here with another wavelength, so you might add this one with that one, you can arrive at something which looks more like the second diagram here. That's a better approximation. If you keep adding on sine waves of a certain wavelength, you can eventually get, by a stepwise process, by adding terms onto the series, something which is a good approximation to that square wave. So this one down here is almost like you've got a load of sines and then added them together by different amounts, different amplitudes, and you end up being able to recreate effectively the square wave pattern. So this is something you can, I'm not sure it's a good idea if you look it up actually. Not yet. They're called, unless you do further maths and you're in the second year, look up Fourier series. It's just a way of representing functions, particularly periodic ones, by a load of sines and cosines. So that's related to what we're doing here, right? Adding a load of waves of different lambdas together to generate a new function which is more tightly packed, which is related to what I'm saying up here. In order to generate a wave function which is highly localized at position x, you need lots of values of momentum, lots of different wavelengths of wave to add to generate that function. Hence, because you've got many values of lambda, that's going to lead to an uncertainty in the value of P, because what value is it? It doesn't have a definite value. I want to do a demo now. In fact, not a demo. I'm not going to play the guitar. I've got a picture of a guitar. That's me plucking the E string of a guitar. Now, when I pluck a string, it can... Have you seen this? If you've done standing waves, you should have done. You get nodes, antinodes, and you can call these different things like the fundamental, the second harmonic, third harmonic, and so on. They're the possible standing waves which can exist on a string. When I pluck an E string, if I let my finger go there, would the string vibrate in one of these patterns?
Yes.
Yeah.
It depends.
Which one?
Depends on the frequency.
The first one.
Does anyone disagree with that? Is there with the first one?
Yeah.
Okay, I'm going to do it. Hang on. Because I want to show you something. Here's a guitar. If I pluck the string, when I misshape it, it doesn't look. In order to play that fundamental purely, I would need to deform the string to exactly this shape, right? Exactly that shape. And even if I use two hands, I wouldn't be able to deform it so that it formed a perfect arc of a sine curve. I deform it. When you deform a string on a guitar, it looks more like that, where your finger, that's my finger, right? You deform it in a weird shape. And what that means is when this string vibrates, it's not in any of those harmonics exactly. How you have to describe the string as being in a combination, some combination of all of the harmonics. That is why a violin playing C sounds different from a guitar, which sounds different from a piano, which sounds different from a ukulele playing a C, because there's a slightly different mix of all the harmonics really within that sound. Mathematically, to describe the oscillation of the string, you have to add all those together. I can prove this to you. Do each of these have a different wavelength?
Yeah.
Yeah. I'm not going to derive the equation for them. They've got a different wavelength, different frequency. Look at this app. This is pretty cool. This app will allow me to, you see here where it says audio spectrum, on the right, display the frequency spectrum of an audio signal. If I select that and press play, oh, is it going to work? Or maybe it's screen sharing that's not letting me do that. That's annoying. What's the best way of doing this? Okay, I'm going to have to rearrange this because Zoom isn't allowing me to share my screen and show you what's on the iPad at the same time. Therefore, I'm going to stop sharing my screen and I'm going to point the iPad at the camera. Right, this is like proper improvisation here, right? So look at, this might not be incredibly clear. Audio spectrum. Why isn't this working? Hang on. Wait a minute. Maybe I need to completely leave the meeting. There we go. Can you see that? Now, what this graph is showing is the frequency against the sort of loudness. So my voice is quite a complex mixture of different frequencies of sound. I'm going to play the E string. See if you can see a difference in the pattern. I'll try and do it louder. Maybe it's not. Maybe I'll try the high one. Can you see that? You can see peaks. Like there are peaks which are slightly higher. There's a series of peaks which form. Just keep watching. I'm going to hold it closer. You can see that, yeah? Those peaks correspond to all those different harmonics which the string can oscillate in. And this sound I'm playing is a mixture, a different mixture of all of those harmonics, which is why you get spikes at different frequencies. Each of those frequencies is represented on this graph. Watch what happens if I play. Who plays a guitar? Right, if I play a harmonic, so if I put my finger on the 12th fret and play, I play what's called a harmonic. Look at the peak should change. Can you see that big peak in the middle?
Yeah, kind of.
So now I'm playing the second harmonic by making this a node on the 12th fret. I can pick that peak out by making the string vibrate more in the second harmonic shape. It's hard to, you can see it in the middle right here. Whereas when I play this open string, I get that peak, but a load of others as well. So why is this relevant to quantum mechanics? Well, in a sense, the state of the string, when I was plucking it, when I plucked it and let it go, the state of the string was basically in a superposition of all its harmonics added together. So we had a sort of string whose state was described by an addition of all the harmonics, different like states which you could derive. So in a similar way, an electron can be represented by different types of wave, different, if you like, different waves of different wavelength, which correspond to a different velocity or position, momentum. The more of them you add together, the more uncertain you are about the exact wavelength and hence the exact momentum. The more you know, however, about the position. Now, I've realized that I've just gone on for almost an hour. If anyone has any questions, please ask. At the very least, okay, what I hope is that it's giving you a little bit of an idea of what's going on. Certainly in terms of this idea of delta X, delta P, not being able to have both equally small. What I'll do next week, I'll do something completely different. I will write the Schrodinger equation down and solve it for what's called a particle in a box, which is basically if you put an electron or quantum particle and confine it to a region of space. And what I will be able to do is generate energy levels. Energy levels which you have met already if you do chemistry, and energy levels which you will learn about in physics, which are related to atomic spectra. So what I'll finish with is that the energy levels of electrons, the reason why electrons can only form certain energies is that if you take a wave and confine it to a piece of between 2 points, so a string between two fixed ends, you only get certain standing waves allowed. right? The fundamental, the second harmonic, the third harmonic. If you take an electron, which has a wave-like nature, a wave function, and then confine it in an electric potential well around a positive nucleus, its wave function can only form certain functions, okay? And each of those functions corresponds to a different energy level of the atom. Now, yeah, I'm aware a lot of that will need thinking about. Perhaps you just think, okay, that was interesting. I'm just going to leave it now until I've done more physics. If you've got any questions, remain. Otherwise, you can go.